the shaded region stuff, is so that we can get to this thing called linear programming. And linear programming starts to become one of its, I'd say it's probably the first real section that gets kind of tricky that we do. This class kind of has this ups and downs with stuff that seems familiar, stuff that doesn't seem familiar, and I try to tie things together that you have done and you've done fairly decently at, and show you how we can use it in another light. And that's kind of the whole point of this course. So one of the things that we do is, well, obviously, this idea of linear programming. Now, it's all hanger and shade. Would you like your ID? Anyway, so what we do here then is we're going to have, it's a combination. Was it your bus? Today I'll let it be your bus. Because you know why? You were ours. To be honest with you, I have no idea what's even going on. So whatever. I fake it pretty well. So here's what's going to happen. This is this unit is it's a combination of solving systems of linear equations, which was 3.2, and yesterday's shaded region stuff, 2 days of shaded region. We put it all together, and what we're going to be able to do here, and just for idea's sake, we're going to figure out specific points of what I call points of inflection. We're going to kind of rough sketch graphs to figure out certain values of ordered pairs that create boundaries. And that's what constraints do. Constraints, think of it as your boundaries. You're going to figure out a specific boundary area within a graph. Those boundaries are going to give you ordered pairs, x's and y values. Those x's and y values are going to be used into what's called like some sort of a function that we're going to look to either find a maximum or a minimum of. These are going to be like your real world style problems, believe it or not. If you are selling apples and oranges and you have certain profit margins you want to reach and things like that, this is the type of things that you're able to do with it. So let's look at the idea of how it starts with. Yeah. If it doesn't work, just kick it really, really hard. Bless you.
Throw it away. Extend the page and give it off. Extend the page.
That's really not good that it doesn't do that. So anyway, so let's use these four equations to create the boundaries. Now, we kind of alluded to a little bit of this the past few days of what it looks like when we have the those two values. The x is greater than or equal to 0, y is greater than or equal to 0. That tells you something important about the graph, the way it's going to look. It tells you where it's going to be located. Where is this going to be located? First quadrant. You're not stupid, you just made a mistake. So this is what we call a first quadrant problem. The reason that it's a first quadrant problem is because the values of x are positive in the first quadrant. That's what we're looking for here. And the values of y are positive in the first quadrant. So that's why we call it first quadrant problem. So we know that's going to be going to the right and up. We okay with that? We had a few of those in the past couple of days for the graphs. So that shouldn't have been a big deal. The next thing we have to do is work with our quick graphs. This is the idea where we had all of those, I was showing you guys that it was super, super easy to graph things. via their intercepts. And you're right, block one of them and solve for the other. Very good. So if I cover up the x value, solve for y, what's my y-intercept? 5, good. Can I just say it's about here? And I put the ordered pair in at 0, 5. I do the other thing, and it tells me my x-intercept is where? At negative 15. Now, I know a negative 15 is going to be beyond my graph, so I really, what's going to happen then, it's going to do this. Are we okay with that? According to the first two constraints, x is greater than or equal to 0, y is greater than or equal to 0, it's telling me that I don't have to worry about any of that graph that fell into the second quadrant. That's what that means. Okay? But now I have to figure out what side to shade. So I still do the same test point idea. What's bless you? What's 0 plus 0? 0. So is it true or false at the origin? It's true, so it's going to shade downward. Good. And again, this is the reason why I'm drawing those arrows. Remember I started doing that a little bit more yesterday in the past couple of days just by pointing direction? Because it's going to be a lot cleaner as you go along. Okay. And then lastly, I have the graph of 2x plus y is less than or equal to 12. X-intercept at 6, y-intercept at, good. So we'll say y-intercept here is 12, so it's at 0, 12, and then 6, 0. Connect the dots, la, 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 la. And then notice those last two graphs intersect, don't they? Those two graphs intersect. Oh, we got a shade, forgot. What's 0 plus 0? Is 0 smaller than 12? So it's moving inward. So right now we have this four-sided figure. Do you see that on the interior there? I have this four-sided figure, and I have what are called 3 points of inflection. I need to find the fourth. The fourth point is located here. I need to figure out what that ordered pair is. Well, in order to figure out what that ordered pair is, I'm going to use the same math that we did last week by solving a system of equations. Oh, actually, it was this week, wasn't it? Holy cow, that seems like so long ago. Anyway, so we're going to solve a system of equations. We have to solve that system. Okay? Now, when we do figure out this the solution set here, when you do that, all you have to be able to do is treat it like you would a regular equal sign. You don't have to worry about the inequalities when you're solving the system here. You're just treat it exactly like you would as an equal. So I'm going to put it on a separate page and just dual screen it so we can see it. So I have negative x plus 3y is 15, and then 2x plus y is 12. Now you have to make a decision on how you want to solve that problem. You can do linear combinations, eliminations, substitutions, whichever you like. What I'm seeing, what I think, is I would move the x and move the 15 and say 3y minus 15 is x. I think in my mind, since that x was negative to start with, if I move it real quick, I can use substitution. Okay. Do I have to use that method? No. Could I multiply the top one by 2 and just add them together? Absolutely. That would work as well. But for some reason, my brain always, whenever I see a negative variable with a coefficient of 1, I'm always thinking, oh, I'm just going to move it and just use substitution. Don't know why, just how my brain is wired. We all know that's a little bit. So if I do 2 times the quantity, 3y minus 15 plus y is 12. Distribute out, you get 6y minus 30 plus y excuse me, is 12. Moving things around, what do you get? Very good. You're going to get 7y is 42 by moving things around. And you're right, y equals 6. You okay with that? if the y value is 6, what's going to be my x value? Excellent. The reason we know that's going to be 3 is because we take the value of 6 right back up here. 3 times 6 minus 15 is 3. And that gives me my ordered pair here at 3 and 6. What this section does, what this section starts out as, is nothing more than the combination of what we've done for the past 4 days. It's just all in one section. Okay? So what you're going to be practicing is everything we've done for the past 4 days. I know, I'm sorry. I'm sorry. But how about this? Not only will you practice what you've done the past 4 days, I'm going to add one more step to it. Well, you know, it's okay. We'll be all right. We'll be okay. I promise you. Have I lied to you yet? When? There will be, yes. But you'd be surprised that once you get through the stigma of a word problem, that they're not that bad. Right? She's like, all right. We all right? All right, let's look at another one. So I'm going to add a step. I'm going to add a step and talk about what's called an objective function. An objective function, to start with, is going to be some function that they give you. Okay? For some reason, they use the letter C for the objective function. Why? A lot of times it's like a cost thing. You're trying to maximize a profit, things like that. What we're going to do is we're going to find what's called the maximum and the minimum of an objective function. By Monday, we're going to develop our own objective functions dependent upon a word problem. Okay? But for right now, they're going to give this to you. So we still have our constraints. We're going to find the maximum and minimum of an objective function subject to the following constraints. What that means is maximize the points of inflection that you create with those graphs. So it's just more words for something that we've done. Why, hello. How are you? Excellent. Have a great day. I need a better high five than that. Come on. Come on, get the elbow in. There it is. That's right. I'm sorry. Shut up, yeah. Yes, sir. Oh, Jared Schultz. The other one. Oh, that's right, there's 2 Schultz. I forgot about that. Sorry. I know. Hey, I'm learning, all right? All right. So, where is this problem going to occur? Very good. It's going to be first quadrant problem. Are we okay with that? All right. We have a first quadrant problem. I have a first quadrant problem, and then I have to do the x and y intercepts out of x plus 8 is less than or equal to 8. X plus y, excuse me. So if I have x plus y is less than or equal to 8, what are my x and y intercepts? They're both 8. Is everybody okay with that? I want to make sure I start with something really, really, really easy for you. Bless you. 8, 0, and 0, 8. Is it moving inward or outward? Inward, very good. So we get we wind up with this region here as our, what we call a favorable region. It's a triangle, very good. So what we do next is we list we list our points of inflection. We list the parameters of the ordered pairs where it changes direction, or your vertices, if you will. You list those out. So when we do that, we get 0, 0, 8, and 0, and 0, and 8. We take these ordered pairs, and we're going to substitute them into to figure out which one gives you the maximum and which one gives you the minimum. I'm going to guess you're right. So here you get 3 times 0 plus 4 times 0, which is 0. All right, way to go, guys. Good work. Next one you have 3 times 8 plus 4 times 0, which is 24. And then 3 times 0 plus 4 times 8, which is 32. Where does your maximum and where does your minimum occur? So your maximum occurs at 0, 8, and your minimum occurs at 0, 0. That's what you're looking at here. Now, what this is going to look like in terms of words eventually, it's going to be like, how many of certain things should you sell to maximize profits? You should sell 8 pens and 0 pencils to make the most money. I'm just thinking of something off the top of my head. Okay? That's kind of where it leads itself towards. Okay? What you're looking at doing is you're taking your graphs of stuff that we've been doing, finding the shaded region, look for intersection of any of the lines, and you're going to list all the vertices that occurs at. Take those vertices and substitute into what's called the objective function. It seems like a lot of work, but it's just a review of everything we've been doing, except for this last step. Oh, my minimum is at 0, 0. My maximum is at 0, 8. And that's, I mean, you can just say, here's your maximum, here's your minimum, and just list it like that if you'd like. And that's fine. Sometimes they'll ask you, what is the maximum value? The maximum value for this function would have been 32. What's that? There are similar ones like that. What's the maximum minimum value of something? A lot of times the ones in the ACT don't use this, they use quadratics. The maximum minimums of quadratics just to correct your vertices. If you know how to use a calculator on the ACT, it's real quick. All right, let's try another one. I'm sorry. I'm a meanie magoo. Quick graphs are your friend. Quick graphs. I don't know how large maybe slow graph versus quick graph. Oh, I'm sorry. I didn't realize that the font is kind of small. The poor people in the back row is hey, tourists! Z! No. Get out of here. All right, so we have the following constraints. We have x is greater than or equal to 2, x is less than or equal to 5, y is greater than or equal to 0, and y is less than or equal to negative 2x plus 12. Now, there's a couple of ways you can go about doing this. Obviously, we're not using graph paper, so we're just going to go ahead and fudge our graph as we go through. So let's do this. We're going to use our quick graphs and kind of think through it. Looking here with just these first 3 constraints, what quadrant should this occur in? First quadrant. Just kind of looking at the values that they're giving you, you should be able to determine that you're just going to have to worry about first quadrant. Obviously, you're not going to be at 0, but you're going to be in that same realm. Okay? So we draw a first quadrant. X is greater than or equal to 2. X equals a number is what kind of a line? vertical. So I say here is x equals 2. And which direction should it be shaded towards? To the right. Okay. Yes, sir. It will be a vertical line. Because that's the next one. No, it's okay. Then I just call that. And then I'm going left. I have a floor at y equals 0. We okay with that? So it's going upward here. So right off of those 3 first graphs, I have 2 ordered pairs. I have an ordered pair at 2, 0, and 5, 0. Very good. Everybody see how that works? All right, so I have one at 2, 0, and 5, 0. Now the next graph is written to you in slope-intercept form. Now, how could you manipulate that to go to quick graphs real quick? What would be easier? Yeah, move the 2x over. So this is the same thing as saying 2x plus y less or equal to 12. Don't you agree? Now, by doing that, it's easier to graph via quick graphs. What's your y-intercept? What's your x-intercept? 6. Oops. And then I have to connect those two. What direction do those go? Downward. Very good. They're moving inward. 0 plus 0 is less. It's moving inward. Okay? Are we right with that? All right. For $1 billion, what shape is that? Trapezoid. Very good. You all get $1 million. Now, to figure out where those two points occurred, don't you know what the values of x is already? Yeah, because those x values are on vertical lines, which means so that means that my value of x stays constant on a vertical line. So I know the x coordinate here is going to be at 2, and I know the x coordinate here is at 5. Well, all I have to do then is substitute into here to figure out what y is. Pretty nice, isn't it? You're using system of equations with rather simple scenarios. So what is negative 2 times 2? Negative 4 plus 12 is 8. Excellent. What is negative 2 times 5? Negative 10 and 12 is 2. Yeah. So what we've done here, guys, is you have found the 4 points of inflection for these graphs. You've figured out that you've got, those are your boundaries of the constraints. Those boundary points are where your maximum and minimum values can occur. Those will be the ones that you substitute into the objective function. In this case, it's the opposite of x plus 3y, to figure out what gives you your maximum and your minimum value, where that occurs at. So we've got our, this guy. How'd I get 8? I took, you remember this is a vertical at x equals 2? So I put 2 into here. Negative 2 times 2 is? Negative 4. Negative 4 and 12 is? 8. So what we're doing here, Sarah, is we're looking where we're just like we've done in the past when we have the intersection of two lines. We can use many different ways to figure out. In this case, we just use direct substitution. All right. So here we just substitute in their four ordered pairs. We have 2, 0, 5, 0, 5, 2, and 2, 8. Does it matter the order in which you list them? No, makes no difference at all. Makes absolutely no difference. And just basically substitute in. And with any luck, you get, when you substitute, is it negative 3? 3 times 8 is 24. I was thinking, sorry, I was doing, God bless you, 24 to be 22. I was checking to make sure you were paying attention. Excellent work. What? There are no mistakes. There are just learning opportunities.
Oh.
Okay. Which one gives you your minimum? At -5. So my ordered pair here is my minimum. And my maximum? Double duck, quack, quack. Again, I'm in a different generation than you, as you may or may not know. There's this game that old people play. So when my grandparents retired years and years ago, they bought a condo down in Marco Island, which was unfortunately destroyed by the last hurricane. Yes, sir. Anyway, so at their condo complex, they always had, on like Tuesdays and Thursday nights, they always had bingo. So my brother and my grandparents would give us a couple of bucks and we'd play bingo with all the old people. And one of the things that they do is if they said before, then people would say, and after. It was. But one of the things that they did was, when they said I, 22, they'd say double duck, quack, quack. Because if you look closely, they kind of look like ducks or swans, maybe. Look, I'm sharing something of my childhood memories of my deceased grandparents, and you guys are all making fun of me. I'm crying on the inside. But no.
That's my constant mistake, buddy. Join the club.
But no, whenever I see the 22, I always say double duck, quack, quack, because it reminds me of my grandparents. So it's a silly little thing. So there's methods behind the craziness in my brain. You guys are just learning that there's some of it there. Some of you already know, and you're just kind of avoiding it. But yeah, do this one. Most of these, hey guys, this is a great observation. Sarah just said, I really appreciate you're making these things greater than able to, less than able to, because they're solid lines. I'd say 98% of the time they're always going to be solid lines. Okay, it is because you're looking to maximize something. You can't truly maximize or minimize something unless you get to it. I will say one thing. There are times that some of the graphs that you get may not have a ceiling to them, and some of the graphs that you get may not have a floor to them. What that means is that there's no upward, or there's no top graph that cap it off, or there's no floor to stop something. So if that occurs, you might have something that may not have a maximum value. You may have something that doesn't have a minimum value, depending upon the graph. That is an occurrence. It is an occurrence. So let's see here. You guys want you try this one. I'll just stand here and have a tour. Oh, thanks. These things, and I think most of you are on the right track here. What happens with these things is that you always want to figure out where the two graphs themselves run into each other. Okay? You're always going to figure that out. Now, in this one, again, we wind up first quadrant, not a big deal. X and Y intercepts at 5. And I believe this one is moving outward. 0 plus 0 is wrong. X and Y intercepts here. I have an X intercept of 6 and a Y intercept of, was it 4.5? And then these 2 points hit here, and again, it's moving outward. So what happens is, you're looking at this region here. So I need to figure out this ordered pair here. There's only going to be 3 of them that are within the region that you're looking for. Okay? There's only going to be 3 spots that you have to worry about where it runs into. In this case, you got to worry about where these 2 guys intersect each other. So if I'm looking at the solve that system of equations, I'll probably just multiply the top one by 3. Wow. Great minds think alike. So I'll get 3x plus 3y is 15. And now remember, when I'm solving the system themselves, treat it like a regular equality. Don't worry about the inequality portion. So I just subtract all those through, and I get y equals 3. You okay with that? So if y equals 3, x will equal 2. So I have 3 points to check. 0, 5, 2, 3, 6, 0. And I forgot what the function was, 5x plus 6y. And then go from there. So that's how we set these things through. It's the idea that we're taking exactly what we did the past 4 days and just finding the point where they run into each other and substituting into what we call a objective function. I forgot what it was. I object to this thing. So we get 0 plus 30, 10 plus 18, and then 30 plus 0. So I have 30, 28, 30. But remember, in this problem, is there a lid on your maximum? So is there a maximum? No. In this case, there is no maximum. But what's my minimum? At 2, 3 is my minimum. Does that make sense? That's why I was trying to explain to you guys while you were writing that down, how sometimes there's not a lid on the problem. It just goes on through infinity, which means there's no maximum value. You could have the exact same thing if it was flipped around. You could have no minimum value. Okay? Think we can handle about 8 or so of these?
No.
0.5? Sure, yes. Oh, so you have that many tests on Monday? Is what you're saying? Oh, well, I'm not worried about today. You've got a couple extra days to get this. Let's do, we'll do This is, I'll put the PDF file on here, but we'll do it on page 166. I'll upload the PDF for you. So this is 3.4 on page, oops, 166. Let's do 12 through 20 evens, okay? Yeah. And like I said, I'll upload the PDF file here right now so that we can get this thing up. Shh, guys, way too loud.